Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. Today, we are going to continue with the moment distribution. I may have a third or maybe even a fourth one uh, session on frames because in fact, all of the examples we use so far are for beams. So we'll see what happens if we have frames. I promised you that I will get you another example where one end of the beam is not fixed because we didn't encounter that case. On top of that, I threw in something here is that the moment of inertia for part AB and BC is I, but for CD, the longer one is twice I. So how does that affect our calculations of relative stiffness? So let's start by saying KAB. Remember, we said if one end is fixed, this would be fixed, of course, when we break down the beam into three portions, right? That would be fixed, but that because it's at the end, there is no extension here, we see that it's hinged or pinned, right? So instead of writing 4EI over L, we are going to say 3EI over L. Instead of writing EI, since EI is a constant, right? Except for this one. So I'm going to write 1 for I, 1 and 2. And the E is, since it's the same material, same E, there is no reason to write it because we are really not calculating the relative stiffness. No, we are calculating the ratio of the stiffnesses because that would become our basis for distribution as a distribution factor. So I can say here simply 3, not 4, because it's a pinned. So KAB is 3 times I, which is 1, times E, which we divide by, over L, which is 15. So 3 over 15, or 1/5. Notice it has BC with it. So I have to calculate KBC so I can find the relation or the ratio of the distribution between these two portions whenever I have an unbalanced moment at B. So BC is fixed on both sides would be, so it's 4 times 1 times E over L, which is 10. 4 over 10 is 2 over 5. So this is 1 over 5, this is 2 over 5, so the ratio is 1 to 2, meaning for our distribution factor at B, it would be 1 to 2, or 0.33 to 0.67, right? 1/3 to 2/3. Now, let's move to joint at C. K, we already wrote KBC is 2/5. Let's calculate KCD. CD, we are going to say 4. I, no, it's 2I. So times 2 times E, that we'll divide by, over 20. So that would be 8 over 20. You can simplify. Oh my God, okay, it's Siri for some reason. Okay, I'm sorry. Okay, so 8 over 20, which is 2 over 5. So 2 over 5 and 2 over 5. So the distribution factor at C would be 0.5 to 0.5. Okay. Now, the next thing is to calculate the fixed end moments at B, C, D, right? B left, B right, C left, C right, and D. So let's get another color, the black. We are going to say fixed end moment AB, meaning at A in the span AB. I printed out I printed out the fixed end moments for different types of supports as well as what did I do? Okay. For different kinds of loading and supports. You see here I have a pin on one side and a fixed on the other, which is this. It's inverted, but it doesn't matter. So I'm not going to look at those. I'm going to look at these. And the case I have here, a load that is not centered is case 2. And it tells me that the fixed end moment at B, in fact, I should say BA, AB is 0, right? That's a pin. So BA, or sometimes I prefer to call it B left and B right. So I can say fixed end moment B left equals P over L squared. Well, P is 15, L is 15, so over 15 square times B square A, this is A, this is B. So A is 10, B is 5. B square A plus A square B over 2. Okay, B square A plus A square B over 2. So yeah, B square is 25 times A is 250 plus A square is 100 times B is 500 over 2 is another 250. So first of all, 15 and square, I get 15 in the denominator. This is 500 over 15. Simplifying by 5 top and bottom, I get 100 over 3 or 33 kip foot. I'm sorry. But BC and CD should be easier, right? So FEM BC, meaning B from the right, it's W L square over 12. W is 3 kip feet, so 3 times L square is 100 over 12 is 25, right? 100, so 300 over 25, over 12 is 25, right? So kip foot. FEMCB, but this is negative on the left and this is positive on the right. Oops, I shouldn't have written here. I want to do the table. Okay, it's done, unfortunately. In fact, I printed 2 copies of it. So here I will do the table and find the balance moments, and here I will draw the shear and the bending moment diagram. I don't know if that would be enough. I don't know how many iterations we'll have to go through. Sorry, guys. FEM member DC. We already did. We said BC and CB. Now we are going to say CD. Yeah. So CD. Same thing, it's 3, but now times 400, which is L square over 12. It's 4 times more, so it's negative 100. Okay, foot. And FEM DC would be 100. Okay, foot. I may have to use this for the table and get a new paper for the shear and bending. Yeah, I think let's do this for the calculations. Notice that at D, there is a cantilever on the right, and it produces a moment. 20 times 3 is 60. So I can say fixed end moment DE is negative 60 kip foot. And that's everything I have. So let's get the other copy. And we don't need the cantilever now. And that's why we assume this is fixed, by the way. Some people will say, but isn't that the end point? No, it's not. there is a cantilever. That's why it's not end. If I didn't have that, then both of these would be similar, and I would say 3 times 2 over L for the relative stiffness. Okay, so here is point A. It's B. Oh my God. I remember I added the letters after I made the copy. I said, wait, I forgot to write A, B, C, D, but I didn't realize it was after the fact. So let's add them up here, A, B. So I remember the dimensions, but not. Okay, so again, we are going to have the first 2 rows. We can assume this is the first row. And I have the distribution factor. Then I have the FEM. And then I would start the distribution and the carryover. Let's do the first couple. I don't know how many, but definitely it won't be 1. There is no reason to write anything here, right? So I have 0.33, 0.67, and 50-50, right? Yeah, 1/2, 1/2. Oh, what am I doing? Yeah, this is 0.33. Why am I doing that? And this is 0.67. This is 0.5 and 0.5. For the moments, I have $33.33, well, same as the ratio. And then negative 25, positive 25, negative 100, positive 100, and negative 60. So let's go over distribution and carry over. When I come here, the difference is 8.33, right? So it's like we can write 100 divided by 3 minus 25. So that's 8.33. But the balance would be negative. So let's divide by negative 3, because that's 0.333, but negative. So that will tell me negative 2.78. And this would be twice as much. So you multiply by 2, you get negative 5.56, right? If you make it 5.6, they add up to 0.34. So let's make it 5.5, just so that the sum would be exactly 0. Notice you cannot get it exactly unless you use fractions and keep going. This is negative 75, right? Negative 100 plus 25 is negative 75. So they divided as 37.5, 37.5. Here it's 100 and negative 60. Notice that all of it will go to the fixed part. The moment here would always remain negative 60, no matter what happens, right? Because calculating from the right, this is 20 times 3 is 60. So the difference is 40, so you get negative 40. And we are done with the distribution. Of course, you could have found the moment here and then subtracted because it's 0, like the distribution factor, and you will end up with 0 anyway. It's a waste of time, right? So now we are going to do the carryover. This one will not give anything, but these two will reverse. So this would be negative 2.78. Notice the same as that, because it happened to be that the ratio is 1/3 to 2/3. So this is half of that, and you distribute half, or you carry over half. So this number will always come here as negative 278. But 37 and a half will give me here 1875. The 37 and a half will give me 1875. And the negative 40 will give me negative 20. Okay, let's move to the next step. I have 1875 that will be distributed between these two. 1/3, negative 1/3 goes here and negative 2/3. Well, this number is divisible by 3, it's 6 and a quarter. So really, negative 6 and a quarter comes here and negative 12 and a half comes there. This one is negative 22. So let's take this number, multiply it by negative 1 to make it positive, and then add 20 to that because I want it positive, right? It's going to be divided equally. So divide by 2, I get 1139 and 1139. All of this goes here, so it's negative 1875. Because eventually I have to end up with 60. Okay, let's take a carry over. This number comes here, as we said before, just because the ratio is 1 to 2. So negative 625. This will bring here negative or positive, no, negative 5, no, positive. Why did I say negative? Negative positive 569. In fact, 695, but we are going to use 2 decimal places. It's good enough. Half of that, again, is the same as that. So this also be 1139. And this will give me negative 938 if you use 2 decimal places. 87 divided by 2. We're gonna use 2 decimal places. So negative 938. Okay, so we are going to do another one. Distribution, carry over. Okay. This is not divisible by 3, but 569 divided by 3 is 1.9, I would say. So negative 1.9 here. And if we say 3.8, we're going to say negative 3.79. So they add up, no, 8. Sorry, I meant to say, yeah, so 79, not 3.8, so that they add up to 569. So we get exactly 0. Of course, all of this is approximation. Now, for this guy, I have the negative 930. Oh, let's write it 938. And we're going to add 625. And then we are going to divide them in half. So you get 7.815. So 7.82 and 7.82. Well, slight difference here. And we are going to do the distribution. So negative 1.9 will come here. And we said, yeah, half of that is 391. So 391 comes here. 391 comes here. And didn't do anything else, right? Yeah, we forgot to write negative 1139 here. And I said something is missing, right? And that would be half of that, which is 560. It's the same thing as half of that. So, no, I'm sorry. This is half. Why did I say? This is half of that, 569, as usual. So this would be negative 569, and half of that will come here. So negative 2.8. let's say 5. And that's the second or the third iteration. Still are in the 2, so next time probably we'll go less than 1 kip foot, so we can stop. I wanted to do that on the previous page, but unfortunately it's not working. It didn't work. I messed it up. We'll see. Okay, 391. Let's say 3.9. So I get negative 1.3 and negative 2.6. These two, 285. So 285 plus 1.9 divided by 2. It's 238 and 2375. 238, 238. And this will go down as negative 391. So that's the distribution. This is a carryover, half of that. So negative 1.3, 1.19, 1.19, and negative 195 or 96. I don't know which one. Let's make it 95. Oh my God. I think still in the 1. So let's do one last one. Oh my God. Okay. Distribution, carry over. This is negative 119. Here I have 119. So 119, oops, I'm sorry. It would be 0.37 or 38 divided negative 396. So let's say, I don't know, 0.4 and 0.8 or 0.4 and 0.79. It's approximation. Here I have negative, no, I'm going to use it positive, 1.3, and this is the negative. 1.3 plus 195 divided by 2 is 1.63 and 1.63. And maybe we stop here. After that, it would be 0.8, and you distribute that, it would be, I think this is good enough. It's a good approximation. Again, it's not ideal. If you use a computer, you can get it. But eventually, really, does it matter? So when you do your design, if the moment is like 74.1 or 74.2, that make any difference? No. You usually round up when you find, say, the depth of the beam, and you get like whatever 52.7 centimeters. You're going to round it to 55, right? You will not do 52.7. How can you perform that? So anyway, let's delete those. Okay, so I start here with 3333 minus, well, it's not exact, it's 2.7778, so it's not, minus 625 minus 1.9 minus 1.3. What did I do? Okay, minus 1.3 minus 0.4. So I get a moment of negative 9.3. Because it's rotating. Oh. Okay, now let's calculate the 2 moments here. Should get the same result here. Negative 25 minus 5.55. So we are just checking. We are going to use the same number. Plus 1875 minus 12.5 plus 569 minus 379 plus 391 minus 2.6 plus 119 minus 0.79. No, something went wrong. Here I had 8. This is factor. This is factor. No, it should be correct. I did something wrong in my calculation. So I said this minus 276 minus 625. No, it's not the answer, so forget about that. Let's just check in. Okay. Negative 25 minus 555 plus 1875 minus 12 and a half plus 569 minus 379 plus 391 minus 2.6 plus 119 minus 0.79. Okay, so I calculated this incorrectly. 33 3 minus 278 minus 625 minus 1.9 minus 1.3, oops, minus 0.4. Yeah, I don't know where I got that, and it should have been positive anyway. Sorry, guys. So 20.7, negative 20.69. So 20.7. But that's how you should check your answer, because if you click the wrong button, you just want to make sure which of the two is the correct one. I'm sorry, guys. I should do better next time. 25 plus 37.5 minus 278 plus 1139 minus 625 plus 782 minus 1.9 plus 238 minus 1.3 plus 163. So 73.49. This is negative, of course. Let's try negative 100 plus 37 and a half minus 20 plus 1139 minus 938 plus 782. Hopefully it will be correct. We don't want to waste time just counting numbers. Yeah, 73.46, again, for approximation, so negative 73. In fact, we can say negative 73.5, just so we use a single decimal place, and it would be. And finally, here, you don't need to do any calculation, because these two cancel, these two cancel, these two cancel, these two cancel, and you get 100 minus 40 is 60, and this is negative 60. So now we are done with the distribution. Next step is always to find the reactions at the support. So how do we do that? Let's look at AB. Here is AB. I have a load of 15. I have a pin. So I will have A sub Y. I have a fixed, that would be a fixed support. So I have this and a moment. So this is BY. I'm going to call it BY left, because there is another load coming from BY right. And the moment we said is 20.7. And the distance is 5 feet, 10 feet. So we can take the moment about A to find BY left. I'm not going to write it. It's just quickly. I'm going to say 20.7 is negative. Notice negative, negative, positive. So instead of saying negative 27 minus that plus the No, I'm going to move them to the other side. And I say 15 by equals 15 times 10 plus 20.7, right? So 20.7 plus 150, that's the negative moment produced by the couple as well as the force. And that should equal 15 times by. So if I divide that, I could have put them between parentheses and divide by 5, I get 1138. So this is 1138. Now, sum of the forces in the y equals 0. If I subtract that from that, I get 362, right? Yeah. So that's AB. I already found that. Let's go to BC. Same thing. Notice the I or the two I don't matter here. So here is BC. So this is BY right, and this is CY left. I have a load, this is 10, and this is 3 kip per foot. There is a moment B here, which is 20.7, and there is a moment here, 73.5. Okay, so I'm gonna do the same thing. I'm gonna, everything is going clockwise would be considered positive in this case. Counterclockwise would be negative. Why? Because I moved them to the other side of the equality, just to save time. So between parentheses, I can say 73.5 minus 20.7 plus 3 times 10 times 5, meaning 150. And I'm going to divide this by 10. So I got 20.28. The sum of the whole sum of the force in the y equals 0. I have 30 kip going down, 20.28, so this is 972. So now the reaction at A is 362 kip. The reaction at B would be the sum of these two guys. 38 and 72 is 110, so I will get 21.1, right? 1138 plus that 30. What? Oh, I added the, oh, I'm sorry. Okay. 11 plus 972. Yeah, it's 21.1 kip. Now, let's take the third bay. But here I'm not, it's easier to draw everything. So I would have to say, I have a CY, right? Then I'm going to say I have a DY and a 20 instead of using the moment. You could, but I think it's easier to do it this way. And this is 20. And this is 3. So like we did before, I'm going to open parentheses and say the moment produced, oh, and the moment here, 73.5. So 20 times 23 plus 3 times 20 times 10, so 200, minus 73.5 divided by 20 to get the dy. 49,325, 49,325. The sum of this is 80, so 80, right? Yeah, 3 times 20 plus 20 minus the 49, so I get 30.675, 30.675. If I add that to the CY left is 20, so plus 20.28, right? That will give me 50.955. So let's say CY is 50.96, And we can say 49, the D is 49 point. We want to make, wait a second, we want to make the sum of the forces to be exactly equal to external loads. So we will have to do some approximations, unfortunately. Okay, so this is 2 and 6. So, okay. Okay, it's better to say 362 plus 21.1 plus 5096, and then subtract those. I'm going to subtract the total load. I have 90, 110, 125. So I will get it in negative. So this is 4932. Just so that we end up with exact value. Okay, so now, unfortunately, it took so long. I'm sorry, but that's how you do it, right? So let's get a new paper and draw the shear and bending. Let's do that here. Up to scale. We don't have time. I don't want to waste your time. So here is the reaction was just 362, right? And then I have 15, and then I have the B 21.1, and then I have the distributed load 3 kip per foot, and then I have the CY, which is 5096, and then I have another 3. This is 20, and the reaction here is 4932. Then I have a load of 20. So I'm trying to do it fast. Let's do the shear force diagram. So easy. Hopefully the math we did wasn't wrong. So with the bending moment, it will close. Okay, so I go up 362, then stays 362 until I come here. And then I go down 15s, and we said this is 1138. I'm not going to draw to scale because I may not have enough space. 1138. And then I'm going to go up 9.72. Right, the difference? I think so. Again, I'm going to make it slightly higher than that, but not much higher because I don't have space. So I'm going to say, what did I say? I forgot. 972, right? And then I'm going to go down 30 to negative 2038. Again, that's not to scale, but I went down 30, so this is 20.28, right? And then I will go up Well, I don't have enough space, so I'm going to do it like that and assume this number. Again, guys, I'm sorry, I don't have enough space. This is 30 point what 68. Then I'm gonna go down 60. What is that? 2932. And then I go up 4932 to exactly 20. Maybe say this is 20 and this is 0, positive, negative, positive, negative, positive, negative, positive. Bending moment diagram would be even worse. I should have solved this problem and found out, how much this, like, what are the numbers so I could have scaled it better. But unfortunately, I did it on the fly, so that's why we had. Or maybe a new page. I'm going to use a different color, so even if they intersect, we see that the purple is the shear force diagram, or maybe whatever, the green is the bending moment. I start at 0. This distance is 10, so I will go up linearly to 36.2, right, times 10. And then I'm going to go down 57.9, 56.9. So 36.2 minus that, of course, that will give me 20.7. Then I will go up that. We need to find that distance, right? So how do you find that distance? If this whole thing is 10, you divide 972 by the sum, which is 30, and then multiply by 10 to get 324. So that distance, of course, that's easy to calculate without a calculator, and that would be 676. This will always be 1/3, not always, but in this case, it would be 1/3 because, yeah, and that slope also, this distance would be 1/3 of that. So I don't really need a calculator. So we are going to say we are at negative 20.7, right? I'm going to add half times 324 times 972, and I will get, oh, so we won't get up to the 0. We are still in the negative, like -5, right? Then we are going to go down. So -1/2 times 676. In fact, square times 3, we could have said 28. Ooh, I will go down to 73.5. This distance is 10 point, what, 23, roughly. And this would be 1977. That doesn't make sense. I don't think we'll go back to 0 because we'll go down even more. That's the 20.7 is correct because we had this 20.7. The 73.5 is correct because we had that. That's how you check, right? If you did a math error. But for some reason, it seems like I shouldn't go less than that because I will go up only 60. So that should be 60 here, -60. But since this distance, oh, this is 9, not 9, 19. Oh, I can subtract 20 from 20. Okay, so here I'm going to add 1/2 times 1023 times 30, 68. And that will give me up. That's the maximum moment we will encounter. Of course, nothing to scale. Don't ask me what to scale. It's like, and then I'm going to subtract 1/2 times 977. It's not, of course, that's an approximation because that's not exactly 23. It's 226666. But times 2932, I get negative 59.8, which is the negative 60. And because of the approximations in the table, we didn't get exactly to negative 60, but we are going to say negative 60 and then go back to 0. And finally, we are done. If you want to find the maximum shear force and the maximum bending moment, and you can find the critical sections and you can do your design. But that's how long it took us to solve a simple problem that could have been done with a computer in no time. But again, sometimes they ask you to use a specific method, so that's how you do it. Hopefully it wasn't bad enough. I'm not like proud of it, but I hope you excuse me. Nothing worked with me today. I'm so sorry. But anyway, I hope you understood the methodology and it's easy for you to replicate and do it much better than this, of course. And if you have any questions or comments, please don't hesitate to ask me and I will try to get back to you as soon as I can. Thank you very much and for watching and have a great day. Bye.